In this video, we will continue to discuss logic. By the end of this video, you will be able to determine logical equivalence through using truth tables and working with De Morgan's laws. Truth tables are a vital tool for systematically evaluating the truth value of complex logical statements. Truth tables help us break down a statement into its basic parts, examine the various possible truth values for these parts, and then see how they combine to affect the overall truth of the statement. One primary application of truth tables is in determining logical equivalence. When two statements are logically equivalent, it means that they are either both true or both false under all possible scenarios. In this video, you'll find a step-by-step guide to using truth tables for this specific purpose. It includes concrete examples and practice problems to help you get the hang of determining logical equivalence. By understanding how to use truth tables effectively, you'll be better equipped to analyze logical statements in both everyday scenarios and mathematical contexts. Let's look at three important terms that are foundational to the study of logic: statement, compound statement, and logically equivalent. First, a statement is defined as a sentence that has a definite truth value. It can be either true or false, but not both at the same time. Next, we have the compound statement, which is essentially a statement formed by combining two or more individual statements using logical connectives like and, or not. This allows for more complex assertions and relationships to be explored and understood. Finally, the term logically equivalent refers to two statements that share the same truth values in all possible scenarios. In other words, if you break down both statements into their constituent parts and evaluate them, they would either both be true or both be false for every combination of truth values. Understanding these terms is crucial for anyone wanting to analyze or create logical arguments with precision and clarity. Step 1. The first step is understanding the individual propositions and compound statements you want to compare. This means identifying the basic statements that make up the more complex ones. The clearer you are about these elements, the easier the subsequent steps will be. Step 2. The second step involves listing all possible combinations of truth values for the individual propositions. This usually means creating a table where you can systematically explore every possible combination of true and false for each basic statement. By completing these initial steps, you're setting the stage for a comprehensive analysis that will help you determine whether the statements you're examining are logically equivalent or not. Step 3. Once you've listed all the possible truth value combinations for the individual propositions, your next task is to determine the truth value of each compound statement for every combination. In other words, you'll take the true and false combinations for the basic statements and see how they affect the overall truth of the compound statements you're examining. Step 4. Finally, you'll check if the truth values of the two compound statements you're comparing match for every possible combination of basic statement truth values. If they do, congratulations, you've established that the statements are logically equivalent. By following these steps, you can use truth tables to systematically analyze and compare complex logical statements, making it much easier to understand their underlying structure and relationship. Let's look at an example using two compound statements: if P, then Q, and not P or Q. Step 1. Our first task is to identify the individual propositions involved. In this case, they are P and Q. These will serve as the building blocks for our compound statements. Step 2. With two propositions, P and Q, we have four possible combinations of truth values. Here you are just writing out a list of all possible combinations of truth values for P and Q. You can visualize this by creating a table to keep your list organized. For proposition P, it could be true or false, and Q could be true or false. When you combine the possibilities for P and Q, you get 4 possible combinations of true and false for P and Q. P could be true and Q could be true. P could be true and Q could be false. P could be false and Q could be true. Last, P could be false and Q could be false. By completing these steps, you've set up the foundation to evaluate the truth values of each compound statement for all these combinations, which will help you determine if the two statements are logically equivalent. Step 3. After setting up the truth value combinations for P and Q, we evaluate the compound statements if P, then Q, and not P or Q by following the same process of listing out all of the combinations based on the values in the P and Q columns. The statement if P, then Q is written as is false only when P is true and Q is false. This is because in this situation, the statement is making a promise that isn't kept. It's like saying, if it rains P, then I'll bring an umbrella Q. If it does rain, and I don't bring an umbrella, I've broken that promise. That's why if P then Q is false when P is true, it rains. But Q is false. I don't bring an umbrella. In all other cases, it is true. Another way to think of this is the statement if P then Q does not make any actual claim about the truth of Q when P is false. It only makes a claim about what happens when P is true. So we fill in the columns with true, false, true, and true for if P then Q. Now let's look at not P or Q. To determine the truth of not P or Q, start by considering the truth of P. If P is false, not P becomes true, and if P is true, not P is false. The statement not P or Q hinges on whether either not P or Q is true, or both. For example, if P is true and Q is also true, the statement is true because Q is true. However, if P is true but Q is false, then the statement turns false as both not P and Q are false. In cases where P is false, the statement usually ends up being true. This is because not P is true when P is false, making not P or Q true regardless of the value of Q, unless Q is also false. Thus, the truth of not P or Q is determined by the individual truths of P and Q, and whether at least one of them holds true. Step 4. The key moment arrives as we compare the truth values of both compound statements. Since they match in all possible scenarios, both are true, false, true, true, so we can conclude that the statements are logically equivalent. And there we have it. By following this step-by-step process using truth tables, we've successfully determined that the compound statements if P, then Q, and not P or Q are logically equivalent. Truth tables serve as a systematic tool for evaluating the truth values of complex, compound statements based on the truth values of their simpler, constituent propositions. This method is especially helpful for determining whether two statements are logically equivalent, that is, if they have the same truth values across all possible scenarios. So, by understanding how to set up and analyze truth tables, you empower yourself to scrutinize and compare a wide range of logical statements. This skill is not just academic. It's a cornerstone of logical reasoning and critical thinking that has applications in various fields. And that's why understanding truth tables is so valuable. They're a reliable tool for making sense of complicated logical relationships. De Morgan's laws are crucial tools for simplifying complex logical expressions or sets that contain negations. Named after British mathematician Augustus De Morgan, these laws are a fundamental part of logic, set theory, and several other disciplines. Understanding De Morgan's laws can significantly simplify complicated logical scenarios, by transforming them into more manageable expressions. This is especially useful in fields like computer science, mathematics, and philosophy, where logic plays an essential role. In this video, we will delve into the specific statements of these laws and provide step-by-step examples to illustrate their application. By grasping these laws, you'll have another powerful tool in your logical reasoning toolbox, making it easier to tackle complex problems in various contexts. Negation, conjunction, and disjunction are key building blocks for understanding De Morgan's laws. First, negation is simply the opposite of a statement. If a statement is true, its negation is false, and vice versa. In symbolic terms, if a statement is represented as P, its negation would be not P. Second, we have conjunction, which is a compound statement formed by connecting two simpler statements with the word and. If you have statements P and Q, their conjunction would be P and Q. Third, there's disjunction, which is similar to conjunction but uses the word or instead. So if you have statements P and Q, their disjunction would be P or Q. These basic concepts set the stage for understanding De Morgan's laws, as they are essential elements in the types of compound statements that De Morgan's laws help us to simplify. Law 1 states that the negation of a conjunction not P and Q is equivalent to the disjunction of the negations not P or not Q. In simpler terms, if you negate a statement that says both P and Q are true, it's the same as saying either P is not true or Q is not true. Law 2 is the flip side of Law 1. It states that the negation of a disjunction not P or Q is equivalent to the conjunction of the negations not P and not Q. So, if you're negating a statement that says either P or Q is true, that's the same as saying neither P is true nor Q is true. These laws are incredibly useful in a variety of fields for simplifying complex logical expressions. They offer a systematic way to break down complicated statements into simpler, more manageable parts. Step 1 is about understanding the components of your statement. You need to identify the individual propositions, often represented as P, Q, R, etc., as well as the overall structure of the compound statement. This helps you to get a clearer picture of what you're dealing with. Step 2 is all about recognizing the type of compound statement you're working on. Specifically, you need to determine whether the statement is a negated conjunction, a not followed by an and statement, or a negated disjunction, a not followed by an or statement. This will guide you on which of De Morgan's laws to apply. By carefully executing these initial steps, you set the stage for effective application of De Morgan's laws to simplify your logical expression. Step 3 involves selecting and applying the appropriate De Morgan's law based on the type of compound statement you identified in Step 2. If you have a negated conjunction, you'll use Law 1. If you have a negated disjunction, you'll use Law 2. This step transforms the complex statement into a more straightforward one. Step 4 is all about rewriting the statement in its new simplified form. Once you've applied De Morgan's law, you'll end up with a statement that conveys the same logical meaning as the original, but is much simpler to understand and work with. By systematically following these 4 steps, you can effectively employ De Morgan's laws to simplify complex logical statements, making them easier to analyze or implement in various applications like computer programming, mathematics, and philosophical reasoning. Here's an example to illustrate how to apply De Morgan's laws. Our statement is, it is not true that both the sun is shining and the wind is blowing. In Step 1, we identify the individual propositions. Here, the sun is shining is represented by P, and the wind is blowing is represented by Q. Step 2 involves recognizing the type of compound statement we're dealing with. In this case, the statement is a negated conjunction, which can be symbolically represented as seen on the slide. By following these first 2 steps, we've laid the groundwork for applying De Morgan's laws to simplify this statement. We've identified the building blocks and the structure, and now we're ready for the next steps of simplification. For step 3, we applied the first of De Morgan's laws, which says that the negation of a statement that asserts both A and B is logically equivalent to not A or not B. Finally, in step 4, we translate this back into everyday language. We find that our original statement, "It is not true that both the sun is shining and the wind is blowing," simplifies to either the sun is not shining or the wind is not blowing. So we see that both statements are different ways of saying the same thing. This shows the utility of De Morgan's laws in making complex statements easier to understand and work with. These laws are not just theoretical constructs. They have practical applications across multiple disciplines, including computer science, mathematics, and philosophy. By understanding and applying De Morgan's laws, you can disentangle complex logical statements into simpler, more manageable forms. The step-by-step approach we've outlined in this video offers a clear pathway for doing this. So, the takeaway here is that De Morgan's laws are a valuable asset in your logical toolbox. By practicing with different examples, as provided in the video, you can become proficient in applying these laws effectively to solve a wide range of logical puzzles and challenges. In today's discussion, we're diving into conditionals, a cornerstone in understanding logical implications. Conditionals often look like if P, then Q, and grasping their various forms is essential for anyone looking to get a solid footing in logic. Understanding the equivalent forms of a conditional can greatly aid in making your arguments more robust and consistent. It's also crucial for simplifying complex logical statements, much like De Morgan's laws that we discussed earlier. So, in this video, we've prepared a deep dive into the world of conditionals. You'll learn how to recognize them and understand their various forms, laying the groundwork for more advanced studies in logic. In this section, we're breaking down the anatomy of a conditional statement, which usually takes the form if P, then Q. To know whether a conditional statement is true or not, remember this rule. It's only false if a true condition leads to a false outcome. Now let's also introduce 3 related forms of a conditional: the converse, inverse, and contrapositive. The converse flips the original statement around, changing it to if Q, then P. The inverse negates both parts, making it if not P, then not Q. The contrapositive both flips and negates, turning it into if not Q, then not P. Understanding these different forms will help you dissect arguments, simplify expressions, and ensure that your reasoning is rock solid. In logical terms, a conditional statement, if P, then Q, is always logically equivalent to its contrapositive, if not Q, then not P. If one is true, so is the other, and vice versa. On the other hand, the converse, if Q, then P, and the inverse, if not P, then not Q, are equivalents of each other, but not automatically so with the original conditional. Understanding these logical equivalencies is crucial because it allows you to reframe statements and arguments in different forms without changing their truth value, which can be especially handy for problem solving and debate. In analyzing a conditional statement, first identify what is the hypothesis, often denoted as P, and what is the conclusion, or Q. For instance, in the statement, if it rains, then the ground will be wet, it rains is the hypothesis, and the ground will be wet is the conclusion. Secondly, you'll want to figure out which form of the conditional you're looking at. Is it the original conditional, if P, then Q, its converse, if Q, then P, its inverse, if not P, then not Q, or its contrapositive, if not Q, then not P? These steps lay the foundation for understanding the statement's logical structure. allowing you to apply logical equivalencies or reframe the statement for easier understanding or problem solving. In the third step, use known logical equivalences to derive a statement that is logically equivalent to the one you're examining. For instance, the contrapositive of a conditional is always logically equivalent to the original conditional. So if you start with if P, then Q, you know that if not Q, then not P is logically equivalent. Lastly, clearly express this logically equivalent form. Put it in terms that make the logical structure easy to understand. For example, if you've determined that the contrapositive is logically equivalent to the original statement, you could say something like, if the ground is not wet, then it did not rain, as a contrapositive to if it rains, then the ground will be wet. Following these steps systematically will help you confidently navigate the complexities of conditional statements, a cornerstone of logical reasoning. In this example, our original conditional statement is if the sun is shining, then the wind is blowing. Here, the hypothesis, or P, is the sun is shining, and the conclusion, or Q, is the wind is blowing. The statement is the original conditional form if P then Q, often denoted as P arrow Q. Now let's find its logically equivalent form. In step 3, we apply the rule that a conditional statement is logically equivalent to its contrapositive. So we flip and negate both the hypothesis and the conclusion, resulting in the statement, if the wind is not blowing, then the sun is not shining. For step 4, we've established that this contrapositive form is logically equivalent to our original conditional statement. To sum it up, the original statement, if the sun is shining, then the wind is blowing, has a logically equivalent form. If the wind is not blowing, then the sun is not shining. Understanding these logical equivalencies can help simplify logical expressions and clarify reasoning in various contexts. Understanding the logically equivalent forms of conditionals is a key skill for anyone delving into logic or any field that requires critical thinking. By knowing how to transition between a statement and its contrapositive, you're better equipped to draw valid conclusions, understand the nuances of different arguments, and simplify intricate logical statements. This video's step-by-step approach and practical examples are designed to help you apply these crucial logical tools effectively, whether you're in a classroom, a debate, or even problem-solving in your daily life.